So we're pleased to welcome this week Professor Lena Roald from the University of Wisconsin, who will be presenting Burning Issues, Modeling Risk of Wildfire Ignitions and Power Outages in the Electric Grid.
All right,
yeah, take it away.
I can start from there. Okay, great. Thank you, Keith, and thanks for having me. I'm very happy to be here to be able to talk about our work on these interactions between power grids and wildfire ignitions caused by power grids and power outages. And so I wanted to say a couple of words just about how this work sort of fits into this bigger picture of resiliency of the grid. And so when we talk about grid resiliency, we typically talk about it as sort of three different stages. We have a stage where we are trying to anticipate the impact of sort of bad events that can happen in the grid. And then we have a part of it which is about withstanding the impact of those events as they are ongoing. And then we have a third part which is about trying to restore and kind of bounce back quickly afterwards. And so in this talk today, I'm going to touch on kind of several of those parts. So first I will talk about, in the first part of the talk here, I will talk about how we can anticipate wildfire risk and try to optimize our response to that wildfire risk. And in particular, I will talk about how we could maybe optimize the use of public safety power shutoffs to minimize wildfire risk while trying to serve as much electricity to people as possible. And then in the second talk, so this is all about sort of shutting down the grid in order to try and avoid risk. And then in the second part, I will turn my attention to trying to restore the grid once kind of things have settled down again. How can we bring the grid back on again as quickly as possible? All right, so in this first part, where we are going to discuss this question on how to operate a power system in conditions with high wildfire risk. This is based on a paper that I've put the citation on for here, and I also just want to acknowledge the contributions of my co-authors. So Noah Rhodes, who's a PhD student at the University of Wisconsin-Madison in my group, and Louise and Taimo, who's a professor at Texas A&M. All right. So if you first take a step back here and just think about how do electric power lines cause fires. So there's a number of mechanisms by which this can happen, but if you have looked at a power line, you probably didn't see too much indication that that one would start a fire. And so essentially what can happen is that if there's a high wind event or there's you have trees that grow into the power lines, you can have situations where either a power line falls down to the ground and starts creating sparks like what you see in the picture over here, or you could have the situation where you get an arcing event, which is essentially something like a lightning strike, where you have current that flows from a power line, jumps over onto, for example, nearby vegetation, and then to ground. And this also causes sort of a high heat release of current. And so either of those could cause an ignition. In particular, of course, if the vegetation around the power line also is dry and susceptible to fire ignitions. Now, we know that ignition events are not uncommon. So this is very unfortunate. They don't happen all the time, but it is not like a super rare event either. So for example, PG&E reported more than 400 ignition events between 2015 and 2017. And there's been many hundreds more in the years since then. However, this is not just a California thing. In Texas, there's also an estimated more than 1,000 fires are started by power lines every year. So these things, they happen. In some cases, these ignitions then evolve into really large and devastating fires. And so some examples include the Kilmore East fire, which is one of the deadliest fires in modern history in Australia in 2009, which was started by a power line and killed 159 people. We have the Camp Fire in California in 2018, which also, of course, which burned down through the town of Paradise and also killed many people and caused a lot of economic devastation and devastation overall. And then most recently also, of course, I mean, there are so many examples of this that I have to keep updating this slide, very unfortunately. But the Dixie Fire is also a fire that was started by a tree toppling over and falling into a power line, and of course ended up burning close to 1 million acres of land. So this is a big problem, and it's also, but I think it's also important to understand that although there are these really big fires, there's also many small fires that can happen. Okay. So another thing that is important to know about the interactions between power lines and wildfires is that there is an unfortunate effect, which is that power line ignited fires often tend to be large, and this has to be with this has to do with the fact that high wind conditions. So if you have a lot of wind, power lines will move more around, and if you also then have vegetation nearby the power line, it's more likely that that vegetation will, for example, come in contact with the line. You will have trees falling over, or you can have lines that get disconnected from the tower, and these things, they tend to happen more frequently if we have high wind conditions. However, if we have high wind conditions, what can happen is that if we have a lot of dry vegetation, that wind can also fuel the fire quickly and make it spread rapidly and go out of control very quickly. And so here's just some statistics from San Diego County, which show that, these are from 2015, which show that although only 5% of fires started in San Diego County are caused by power lines, they together account for more than 25% of the area burned. So this is sort of, there are these very large fires, but also fires in general can kind of grow large because of this high wind condition effect. And then maybe I don't need to say this, but the wildfire risk is expected to continue to increase in the future as climate change is unfolding. There is an expectation that higher temperature and droughts can lead to more days with very high wildfire risk. Okay, so this is sort of the background, the backdrop here, right? Now we can ask ourselves, how do we now go about modeling and mitigating this wildfire risk and these interactions with the electric grid? So if you think about wildfire risk, we can think about it as consisting of several components. So I would talk about the wildfire risk R as the kind of the combined effect of the probability of having an ignition times the size and intensity of the resulting fire. And so if we look at this, the size and intensity of the resulting fire is primarily driven by the ambient conditions. So for example, is it dry, or what is the kind of the type of vegetation around the power line? And so information about the size and intensity of a resulting fire can be found, for example, by looking at the Wind Enhanced Fire Potential Index, which is published by the US Geological Survey on a daily basis. So you can look at sort of large scale patterns of wildfire risk within the United States. And so this wildfire risk data describes what is the probability, or what is the likelihood that if you have an ignition, that it will grow into a large fire that will need fire suppression efforts, and is then of course also more likely to become a bigger problem. So it is maybe possible here to say that power utilities, they don't necessarily control those ambient conditions, right? They can't say, oh, we want to have rain, or they can't control necessarily the type of vegetation that is around the power lines. However, the thing that they do control is the probability of ignition. And so what they have both sort of a responsibility and a possibility to do is to try and avoid those ignitions from happening in the first place. So let's look at a couple of things here that power utilities can do in order to try and mitigate this wildfire risk. So there are several risk reduction strategies. Some of them involve infrastructure upgrades, vegetation management, or more frequent maintenance. So for example, for infrastructure upgrades, you could think about putting lines on the ground or use covered conductors instead of wire conductors, different kind of things that reduce the probability that you are going to have an ignition. You can go and also cut back trees more frequently to avoid that the trees come too close to the power lines, or also do more frequent maintenance just to make sure that the equipment isn't failing. So the thing about those strategies is that these are, kind of longer term solutions. So these are questions that, these are actions that mitigate wildfire risk because they do reduce the probability of ignition, but they also kind of generally improve reliability of the grid because they are targeted at reducing the probability that we are seeing these fault conditions that cause the fire ignitions. So these are kind of a win-win in both that we reduce wildfire risk and we improve reliability and ability to provide electricity to people. However, the drawback to those strategies is that they require both investment and time for implementation, so they can be expensive. And they are not the kind of things that you can do. If today I'm observing that there's a high wildfire risk, tomorrow I can't really go out and then put lines on the ground and so on. This requires years of preparation. So on the other hand, we have a set of shorter term solutions. So things that can be done if we are seeing that there is a high wildfire risk tomorrow. And so one of the actions that can be taken is to disable automatic reclosers. So this means essentially changing the protection system settings of the grid to ensure that if a line trips offline due to a fault, the line will not automatically try to reclose. So this is something that is commonly used in power grids, but could increase the likelihood that you do get an ignition if you have a fault. Or you have, of course, a public safety power shutoffs, where you essentially go out and you turn off a power line and parts of the grid just to make sure that there is no current that can cause these sort of lightning strike types events or sparks or so on from the power lines. And so these are short-term solutions. So they do mitigate wildfire risk. They are also fast to implement, so you can turn things off pretty fast. The main issue here is that they come at the expense of providing prolonged power outages to people. So in the case of disabling automatic reclosers, if you do have a fault, it's likely that that fault is going to stay there for a long time, and you will have longer power outages. And with public safety power shutoffs, I mean, the whole point is to kind of shut down the grid, and which of course then also leads to power outages for people who rely on electricity coming through those lines that are getting shut off. So that is a really hard trade-off. So let's look at this public safety power shutoff. Of course, I mean, I think many people here on this call are, I mean, many of you are probably much more intimately aware of what it means to live through a public safety power shutoff, because one of the largest such power shutoffs to date in October 2019 also affected the Bay Area and Berkeley. And so this happened sort of early mid-October of 2019. And so in this public safety power shutoff, approximately 3 million people lost power. Power were out for several days in many places. And so this is, of course, extremely disruptive when you have this kind of event. On the other hand, as PG&E went back and walked by all the lines to look at the different to look at the lines and what had happened after the wind event was over that was causing this high wildfire risk, they find that there were 100 locations where there was wind damage to the transmission lines that could have caused wildfire ignitions. And so now you're facing this extremely challenging trade-off, right? 3 million people losing power, 100 wildfires being avoided. Was it worth it, right? And then also we should say that those lines that were shut off, they are not the only source of wildfires. There's also other wildfires that could I mean, other sources of wildfires that could happen at the same time. And in particular, you know, so this is a very hard trade-off to deal with. And so the question that we are trying to answer here with our research is was trying to understand better which lines can we do better in terms of understanding which lines should be turned off. And so in particular, so we went and we looked at, you know, what are the kind of criteria that are in use here. And so this is a figure here taken from PG&E public safety power shutoff policies and procedures. And essentially what you can see here in sort of this public facing document is that PG&E is taking in a whole lot of data and bringing it into their doing an analysis of this data to determine what is the wildfire risk associated with different parts of the network. And so the way, and then if lines exceed a certain threshold, then they will go ahead and they will start a public safety power shutoff. So I, maybe in a somewhat simplified way, would say, kind of characterize this as we set sort of a threshold for the acceptable wildfire risk, and then we are checking whether a line, whether the risk associated with the power line is exceeding that threshold, and if it is, we turn off this line. And so essentially, when looking at this, we are only looking at the wildfire risk. So the other aspect that we wanted to understand here is whether it might be possible to do better. And in particular, would it be possible to do better by explicitly considering the load shed that would result from this public safety power shutoff? Okay, So that leads us to this formulation of this problem, which we refer to as the optimal power shutoff. And I will just say here, I'll be the first to acknowledge that the optimal power shutoff is no power shutoff at all. Like, no one wants a power outage. But the question that we are interested in answering here is, can we find a power shutoff that leads to a significant reduction in wildfire risk while still keeping the lights on for as many people as possible? And so let me just kind of go through the formulation of this problem, sort of to explain how we model this. And so first, let's take a look at our objective function. So you can see here that we're trying to maximize this function, which has two terms. So the first term here refers to our sort of wish to try and maximize the amount of load that we are able to deliver to customers. And so you can think of d tot here, this variable here, as the total amount of power or energy that is being served to customers. And this amount of energy over here, it is calculated using the sum of weighted demand at each node. So essentially, we are looking at the total power consumption that would have been at this node if we didn't have any power shutoff. We are looking at a weighting factor, a W here, which can be used to express load priority. So for example, we can choose to prioritize emergency services or community, or a particular community with specific needs for electric powers. And then we have a variable here, a decision variable XD, which represents the fraction of load that we are choosing to shed at this node in the network. Okay, so this is essentially the impact of, I mean, here, this is a term that we want to maximize because we want to maximize the total amount of power that is delivered. The second part here, we are looking at minimizing wildfire risk. And so essentially the way we express wildfire risk in this case is that we are trying to using criteria for evaluating the risk of individual components in the network. So this would be the risk that each component would be the source of a wildfire ignition. And then we introduce variables that represent whether or not that component is energized. And so in particular, we have this binary variable Z here, that if we set Z to 0, we assume that this power line or so the substation, the load, the line, the generator, that they are being shut off. Or if they are set to 1, then we are assuming that they are in operation, and then we are accepting the risk associated with keeping them there. And then we also have the same expression also here for the load, where again, we are just kind of rating the risk associated with this load by the total amount of load that it is being served. So you could think of this as the risk of serving loads inside the distribution grid, for example. All right, so now we have this objective function where we are trying to maximize the load delivery while minimizing wildfire risk. And so these are these two terms. You can also see I have this factor here, alpha. So alpha represents a trade-off parameter here, which I can vary between 0 and 1. If I set it close to 1, I'm focusing mostly on reducing wildfire risk. If I set it close to 0, I'm focusing more on serving load. And varying between 0 and 1 essentially allows me to explore the trade-off between those two objectives. And the reason also here, I will say that we are using this parameter alpha instead of trying to, for example, express both in terms of monetary value, is just that these are really, really hard assessments to make. So we wanted just to look at each dimension separately. Okay, so in order to understand how the shutting down certain components to reduce wildfire risk impacts our ability to serve the load, we also have to include some constraints that represents the operation of the electric grid. And so I'll just kind of quickly walk through this. So we have a set of constraints that essentially represents component interactions in the grid. So for example, if a substation is disabled, all the components that are connected to the substation also has to be de-energized. So a line cannot be energized and connected to a de-energized substation. Same thing for loads, same thing for generators. We are also looking at, we also include generator constraints, where if a generator is shut down, its power output is set to 0. Otherwise, it is operating within its operational limits. And then we have power flow constraints. So we are representing the power flow here using a DC power flow formulation. And essentially, if we have that, if a power line is disabled, we are shutting down the power flow on that line. It's set to 0. But if the power line is still in operation, we still have to, consider sort of the standard power flow limits on that line. And then we also have a power balance at each node. Okay, so putting this all together, we get this resulting problem formulation here. So we have our objective function, we have expressions for total load served, the wildfire risk, the power balance, the power flow constraints, generation and component relationships. And so this is kind of a large scale optimization problem because it includes constraints for all of these components in the network. There can be many buses, can be many lines, can be many generators, right? And so I also just want to say it's also a mixed integer linear program. So we have a set of continuous variables that are marked in blue on here, and then we have a set of integer variables marked in green. And so for those of you who are familiar with mixed integer linear programs, these can sometimes be hard to solve. So I will touch on the complexity of solving this problem and whether or not that's easy a little later. Okay, so this is our problem formulation. So I want to take you into a little case study over here. And so this case study is considering a case that is sort of a standard test case, the IEEE RTS GMLC network. So this is a network that was developed by the National Renewable Energy Laboratory and includes load data, generation data, and so on. They also included in this latest version of this network, they have included geographical coordinates of this network. And so you can see that this standard test case is kind of located in California. And so in this graph here, I've placed the network. So the network here is represented by these green lines. So they represent the transmission lines and where they cross, this is where these buses or the nodes and substations in the network are. And load and generation are also connected at those nodes. And then you can see underneath here, we have the map. So this is essentially the coast of California here. And you can see that this network sort of goes from sort of Southern California here into Arizona and Nevada. And so what I've also included on this map is these colored parts here in yellow and reddish color. And so they represent different regions with different wildfire risk. So we have the white regions that are low risk, light yellow regions, which are medium risk, darker yellow, higher risk, and then orange are very high risk. And so I will just say here, these are in our test case just assigned a numerical value. So we have 4, 3, 2, and 0. And so it's kind of a unitless wildfire risk, if you will. And then essentially what we do is that we take this data and we estimate the device risk based on its location. And then for the transmission line, we're essentially looking at what are the locations where those lines are going through. And so we are kind of just looking at the cumulative risk for each of the lines. And then in addition, we are also incorporating sort of a risk adjustment based on the voltage level, because we know that lower voltage lines tend to have a higher risk of starting ignition. So in particular distribution lines. And this is due to just the fact that the right-of-ways are smaller, but also because there's a lot more components associated with lines. So there are more things that can fail in the distribution grid. And so the risk factor here is 3 times higher if we are looking at the lower voltage line. Okay, so let's look at some results. So here, this is our original system, which is kind of a high risk case here. The total risk of operation here is this unitless number of about 750, and we are serving 8,550 megawatts of load. Now, when I want to go ahead and I want to solve this optimization problem, I have to choose a value for alpha. And so I start out and I will choose what I will refer to as a medium risk case, where alpha is set equal to 0.01. And then we will see what that looks like. So essentially, if I solve this problem, what I obtain is the solution that you can see here. So this is a map that again shows the network. The actual map is not underneath, but you can see that this region over here corresponds to the region over here. And so you can see that there are many nodes and transmission lines that are marked in green here. Those are the ones that are still in operation. We have also several generators marked in blue here, which represent generators that are also still in operation. And then we have many grayed out elements. So we have grayed out generators, we have grayed out transmission lines. Those are elements that have been taken out of operation, and so they are de-energized. And then you see that there are certain nodes here that have red color. And those red color nodes are nodes where we either have total or partial load shed. And so if I look at the numerical results in this map over here, one thing you can just see is that sort of the lines that are in these highest risk regions, these are the ones that are most likely here to be shut down. And so if I take a look at the solution, what I observe here is that by shutting down this kind of very selective set of components here, I'm able to reduce the risk by close to 60%. And I achieved this by having a very small load shed. So I only shed 10 megawatts of load, which is about 0.1% of the total system load. Also, this problem solves in less than a second. And then if I go and I look at the case where I increase alpha a little bit to look at the case where I will have a lower risk, then the solution that I get is the one over here. And you can see that relative to my medium risk case, I have more nodes where I have red color. So I have more load shed. I have more transmission lines that are grayed out, more generators that are grayed out in order to reduce wildfire risk further. And so essentially here, the total risk in this case is, I'm reducing the risk here by 92%, and the total load served here, and I'm also having but I only get this risk reduction at the expense of having a larger load shed. So here I shed about 15% of the load. And again, this also solves quickly this problem. Okay, so let's look at, so I also just one thing to point out here in this solution is that you can see that there are many nodes that are located sort of, they're isolated, but they are still green. So what we can see here is that although certain nodes are being disconnected from the main grid, they are still able to maintain operation because they have local generation. And so we can kind of roughly understand this as the benefits of distributed generation and the benefits of the grid to be able to sort of split up into different islands when needed. All right, so then I wanted to show you some benchmarking. So I told you about this transmission risk threshold, which is somewhat representative of, or kind of more or less representative of what is happening out there currently. And I also explained to you that this risk threshold only measures the wildfire risk without accounting for the resulting impact on electricity delivery. So what we want to do here is that we want to compare the wildfire risk levels and the total load delivery that we are able to obtain with our with this sort of current practice risk threshold, which only looks at wildfire risk when designing which lines to turn off, and compare that with our sort of optimal power shutoff, where we are looking at the trade-off between power outages and wildfire risk. And so in each of those formulations, we do have a parameter that represents sort of the trade-off here. So in this case, we are varying RL max to get different solutions. Or if I'm looking at the optimal power shutoff, I can vary this parameter alpha as I did before in order to get different trade-off solutions. So let's look at what we get as we are varying those two parameters. So I will plot the results on this slide. So I've not yet put the results on here, but what you can see is that on the y-axis here, I have the wildfire risk. So essentially, the higher up I am in this direction, the higher wildfire risk I get. And the x-axis here, I'm looking at kind of higher load delivery as I am going towards this end. And then essentially I'm plotting the kind of current practice solutions that I get as I'm varying this RL max threshold in orange, and I'm going to plot the solutions to this optimal power shutoff problem in blue. And so what I get as I'm tracing out this optimal trade-off for these different risk thresholds and trade-off parameter alphas, I get solutions that you see here. And so what you can observe here is that the red dots for kind of this current practice, they are always a little higher than the solutions obtained if I'm looking at the blue values here. And so essentially what I'm seeing is that with my optimized power shutoff, I'm able to obtain both lower risk and smaller outages relative to this kind of threshold-based approach. And so, for example, what this means is that if I say that I want to serve at least 8,000 megawatts of load, then I'm able to do that with a lower wildfire risk if I optimize compared with kind of current practice or just using this threshold. Or if I set a wildfire risk threshold at 200, say, then I'm able to serve more load if I use my optimized shutoff procedure rather than just using a simple threshold. So maybe one interesting question here now could be to ask, how is this possible? Like, why are we actually ended up getting these solutions? So one answer is to say we have more information, so we're able to get better decisions. But also let's look at this a little bit more in detail. So in particular, let's look at the risk associated with power lines. And so essentially, if we think about this, we can think about the power transfer on the transmission line as being indicative of how important this power line is in order to bring electricity to customers. And then we can think of the wildfire risk associated with this power line as being, important for whether or not this line is at risk of starting a wildfire. And so if I look at my sort of threshold-based criterion for wildfire risk and choosing which lines to shut down, what I essentially would do is that I just pick a threshold here, say 20, and I keep any line that is below 20, I will keep that in operation. So I'll keep those running and I'll shut down all my other power lines. So I'm just making the decision only based on information along this x-axis. So essentially higher risk means I shut it off, lower risk means I keep in operation. However, if I go to our optimized power shutoff problem, we have more information. So we can also take into account not only how high the risk is of the line, but also how important that line is in terms of providing power to people. And so essentially here you can see I've plotted the risk and the power transfer for all of the lines. So inactive lines are plotted in gray here. They all have a zero power transfer, so they are along the x-axis here. And then all the active lines are plotted in green. And you can see that for a majority of the high risk lines, they are shut down, and many of the low risk lines are still in operation. But what we also observe is that we keep a couple of high risk lines in operation because those are deemed so important for power transfer that they are chosen to be in operation, although they have a relatively high wildfire risk. And conversely, you can see that we have chosen to turn off many lines that were kept in operation before because those have a low but non-zero wildfire risk and maybe are not that important for load delivery. Okay, so this is kind of why this idea of not only accounting for the fire risk, but also accounting for the power transfer is really what enables us to get those better solutions. So one question that I wanted to also talk about here is just like this question of does it scale? I mean, I showed you a very small system here. So essentially we have run some tests for bigger kind of power system test cases, looking at randomly assigned risk values. We've done 20 replications of them just to get a sense of how does this scale. And so just I can sort of report here that most of these systems, they are solved within a few seconds. And so as I said, this is a mixed integer linear program. And so kind of what this is indicating is that probably our continuous relaxation is tight. So our mixed integer problem, when we relax the binary variables to be between 0 and 1, we probably find a feasible solution directly in many cases. However, there are also some outliers here. So those are not necessarily the largest systems, but so sort of understanding like why these take so long time, maybe we will be able to figure it out. Maybe this will remain a little bit of a mystery. We haven't quite figured, there's definitely no like very simple answer to why these solutions are harder to find. Okay. So with that, I'm kind of going to turn my attention from shutting things down, how can we turn lines back on? So we talked about the power shutoff part of this problem. Now the question would be, how do we actually go about bringing the system back into operation? And so here it's worthwhile to note that, you can't just turn a power line back on after you have shut it down like this. You actually, you have to send out a utility crew to inspect the lines before they can be turned back on. And so since this is something that takes quite a long time, and I'm sure that is something many of you might have thought about, that this takes a long time, is that the question becomes, which lines should we actually prioritize first? So what is the priority for restoration here? And so this is, I just again want to say this is joint work with also my student Noah Rhodes is involved in this as well, and then with Carlton Coffrin from Los Alamos National Lab and also David Phobes from National Lab. So we have been working on some methods in order to try and develop scalable restoration algorithms that could be used to answer this problem. So essentially, this question of system restoration, what our goal is here is really to find this best restoration sequence, which maximizes the amount of electricity served over time. And so what you can think about this here is that, again, here I have a little graphic. I have sort of a timeline here on the x-axis. I have electricity served here on the y-axis, and each of these bars represent essentially the electricity that is not being served to customers at any given point in time. And so if I have an outage and I start out by having the amount of electricity not served that you can see here, say then I go out, I do a repair, and I am able to reduce the electricity not served a little bit. And then I go and do the next repair, and I further reduce the electricity not served. And I continue in this manner until I get to a solution where all of my power customers again have access to power. And so you can think about those bars over here essentially sort of as the total size of the power outage. So we want those to be as small as possible. And so the question that we are trying to answer here is just like, how do you pick the repairs? What is the order that you should pick in order to make this small? And I just want to say, so there's a big literature out there on system restoration. A lot of it has focused on sort of restoration after blackouts. This is a little different from the problem that we're looking at here because, you know, in our case, physical inspection or repair is needed. There is also a lot of literature on restoration, which do require physical repair or inspection. And there is a lot of different complications that many people have looked at here, including sort of expanding the scope of this to also include crew scheduling, vehicle routing, consideration of protection system, different switch types. There's a lot of complications here. And this is a really interesting and large set of literature. I didn't even try to sort of do a review here because it would fill the slide very much. So we have that in our papers. So for our purposes, what we are focusing on here is just power flow. And the reason that we are kind of trying to look at just understanding the sequence of repairs and how that is impacting kind of this, the energy that the power system can serve. The reason we are focusing on this problem first is just that it turns out to be really, really hard in itself. So let me talk a little bit about why are restoration problems hard. So when we are thinking about restoring a power system, and you can think about that, you've gone ahead and you've shut down a really large part of your system, you have to go and inspect all those different lines. And so essentially you could think of this essentially as the number of time periods that we have here is more or less equal to the number of components that need repair. So this is of course a simplification. You could have multiple crews that could do multiple repairs in each time period. But again, for simplicity, we are just going to assume that we have one repair in each time period. And so then in each time step, you have to actually resolve the full state of the power system if you want to understand the impact of this repair. And so essentially for each time step, you have a sort of an optimal power flow type problem where you also have integer variables to determine, you know, which lines are actually switched on and off still. And so this is again a mixed integer optimization problem that in structure is kind of similar to the one I showed you before for the public safety power shutoff problem. But however, the issue here is that all of these time steps are coupled. So we have to consider them all together, meaning that our problem is really kind of growing very quickly in scale here. So we have very many different time steps to consider. And so in order to try and figure out like ways in which we can solve this in a tractable manner, there are different things that you can do. First, let me show you. So this is kind of the full problem. This is the AC restoration ordering problem, which includes, you know, our objective function to try and maximize the load served, look at the power flow constraints. We have power flow limits and angle constraints. We have voltage constraints, generation constraints, and then restrictions on the number of repairs that can happen in each time period. So this is for the whole grid for each time period. So it's a really, really, really big optimization problem. So in order to solve this tractably, there's a few things that we can do. So our option number one here would be to use kind of a simpler representation. Instead of using this full AC restoration problem, maybe we can use a simpler power flow representation like a DC power flow or a convex relaxation, like the second order cone relaxation, in order to decrease the complexity. So essentially, as we're going from AC power flow to the convex relaxation, the SOC relaxation, or the DC power flow, we are decreasing accuracy of our model, but we're also decreasing complexity. And the other option that we have is to try and develop some good heuristics that reduce the number of time steps considered at the same time. And I will just say here that sort of greedy heuristics that are just looking at kind of like, let me install the capacity, like repair the component with the largest capacity first. Those have actually been shown to be not very effective. You do need, at least in meshed systems, some sort of information about how power is flowing. And so so essentially here, in one way you can try and reduce the number of time steps that you have to look at the same time, is to sort of first try to identify a minimum set of components that need repair before you can serve the full load. So essentially, in terms of our figure from before, we saw that after a minimum of 7 repairs, we are able to serve the full load here. So maybe we should try and figure out, what are those 7 repairs, and then we can order them rather than try and order all of the repairs. Because as we are doing further repairs, they are needed, but they don't impact our ability to serve our load. And so essentially, if we come back to this figure over here, what that means is that maybe we are able to cut down some on the number of time steps that we have to consider. An interesting side effect of this problem is that in these repairs, essentially what we are doing is that we are trying to figure out which repairs do we have to do to restore power to everyone in the shortest amount of time, in the shortest amount of time steps. So that is kind of a side effect of using this kind of pre-processing tool. Okay, so a few results here. So I'm going to go through this pretty quickly. So first, we can try and ask this question: do we need a detailed power flow formulation? And so in our simulations, what we have found is that essentially too much detail is not always a good thing. So when we are using the detailed AC power flow formulation in our optimization problem, we find that the problem is really, really slow. And also in some cases, in several cases, we also find that this solving this problem actually provides us with a worse solution than using the DC or the SOC formulation, because our optimization solver gets stuck in a locally optimal solution. And so one example of this is the fully damaged test bus case here. So where you can see that the AC restoration ordering in blue here, these bars are higher than they are for the DC and the SOC solutions. One thing, though, I will say is that neglecting reactive power is not always a good idea. And in particular in restoration sequencing, the system is oftentimes under quite a lot of stress. And so solutions based on the DC power flow in very many cases underestimate the energy that is not served. So if we compare, the solution from our optimization problem in blue here and the solution that we get if we do post-processing with an AC optimal power flow, we see that, we are underestimating, how much energy we are able to serve. And this is primarily because the DC optimal power flow lacks consideration of voltage and reactive power. In scenarios where network topology and connectivity is more important, then this problem becomes a bit simpler. So for example, in distribution systems that are naturally radial, then this is a much simpler problem than the DCOPF does. The DCROP does a good job. And then when we come to this minimum restoration set, we find that this problem, you get solutions like the one that you are seeing over here. So if you take a second to look at this, this is the amount of power that can be delivered over different time periods. And what you see here is that if I use the minimum set restoration problem, I get the solution in dark green. And so you can see initially I have the same solution as when I solve for the full restoration problem. But with the minimum set, I then have sort of 3 periods here where my load served is kind of constant and relatively high. Whereas with the full restoration one, I'm lowering the amount of energy that is not served quicker, but I do have an extra time step where people do not have access to power. And so essentially using this type of minimum restoration set pre-processing means that we are minimizing the time until everyone has power, but we are also leaving some people longer in the dark. And so you can really start asking questions here about, is this a better or a worse solution? I am not sure, because, what is a fair thing to do here? Is it fair to try and bring everyone power as quickly as possible? Or should you kind of focus on getting power to as many people as possible, as early as possible? So, trade-offs that can be considered. All right, so that brings me to the conclusions. In short, in summary, I had 2 parts of this talk. In the first part, I tried to show you what I believe is the first, at least public optimization model to determine locations of public safety power shutoffs. And in the second part, I was trying to give you a brief overview of our development of scalable algorithms for power systems restoration. I would like to leave you with some insights that I believe are important here. So for example, what we see is that accounting for both wildfire risk and power outages leads to better solutions, but it also leads to a more complex problem. So of course, this is where we hope that the type of research that we're doing can help in providing the methods and tools to actually take more of this information into account while making those challenging decisions. And then also another thing that we are seeing here is that the important decisions that are being made here, such as what is the right trade-off between wildfire risk and power outages. As I showed you, there's a whole trade-off curve that you can pick solutions from. And what is the right trade-off? Or in the case of restoration, how should we actually go about prioritizing those restorations? Those are probably not decisions that should be left to utilities or engineers alone. And so I think that I hope that these are kind of important questions that maybe needs more attention. And for us as engineers, I mean, thinking about how we design our algorithms in order to try and improve kind of different aspects of the outcomes that come from these the optimization solutions is quite important. And so with this, I mean, this is kind of a little bit of an outlook here. So this is just the first step. I mean, what I have presented here, we are kind of continuously now chasing kind of how can we create better models here. In particular, our models do not really go into depth about regarding distribution systems. So we are kind of trying to understand, you know, how do we extend these kind of methods into distribution systems. It's also interesting to say that, you know, particularly in the public safety power shutoff problem, how do you capture relevant timescales that can go from we only consider one time step, but the considerations here could really go from several days to several years. We are also interested in understanding and modeling the post-ignition system operation. So what happens if there's actually a fire? And then, of course, there's a lot of different things that can be included here. You know, for example, microgrid capabilities, as I said there, maybe we also need to think about reactive power in that setting. And then we are also trying to understand, you know, how can we get better input data here? So one thing is the modeling of wildfire and wildfire ignition risk. So here on the right, I'm showing a picture of, this is the grid in California, not a test case, but the actual grid obtained from the California Energy Commission. And it's overlaid on one of these wildfire maps from the US Geological Survey. And so we're working on trying to understand how we can bring all this data into our models so that we can, you know, start running more realistic analysis. And then we're also modeling, trying to understand how to better model the impact of power outage impact, have better models of power outage impacts, which can include also aspects such as social vulnerability and energy justice, and whether these are how we can try and bring those considerations into the work that we are doing here and design our algorithms to provide equitable outcomes. And so that is there we are looking at census data and trying to understand how we can bring that into our models. All right, so with that, I kind of want to say, you know, if you want to test this out, we do have our code that's mostly released on GitHub. We have our Power Models Wildfire package, which has the code associated with the wildfire risk work here. We are working on Power Models Restoration in collaboration with Los Alamos National Lab. So you can also find the link there. And the plotting in this, the plots that I've shown you of power systems here are from powerplots.jl, which is also a package that we are developing in my group to try and, you know, help us understand what's going on in these test cases. So yeah, also freely available, and we would really appreciate anyone's feedback and contributions there. So yeah, so with that, I think I am done here. I would just like to say thank you, everyone, and any questions?
Wow, that was a really great talk, Professor Roald. I see some claps and then also some comments. So I'm going to turn off the recording for the question section, but I think we'll have a lot of questions. So